So we've already talked about z-tests or t-tests, depending on the scenario, to compare the means of two different groups, right? Remember, we tested the null hypothesis that the means were equal against the alternative that they were not equal, right? If the difference is 0, that means that they're the same, right? Against the alternative that they're different. This would have been a two-tailed test. We did talk about having, one-tailed test to the right or to the left, but this here is a two-tailed test. And depending on whether we were testing about one mean or two means, or whether we knew the standard deviation or not, generally these statistics came under this form: the estimate of our parameter minus the value of our parameter under the alternative hypothesis divided by the standard error. And you can think of this as kind of a ratio, right? How big is the difference divided by how big the standard error is. Okay, and we talked about how to get p-values for z and t statistics. Now, if we want to compare more than two groups, so 3+ groups, we're going to use this new technique called ANOVA. The null hypothesis for ANOVA is that all the means for all groups, in this case there's k groups, but k could be really any positive number bigger than 2. The null that all the groups have the exact same population mean against the alternative that at least one mean is different. And the way that we get at this is a new type of test statistic called an F statistic. And it's going to be also made up as a ratio. On the top, we're going to have sort of the variability between the different groups. In this case, there's k different groups, divided by the variability within groups. And it's going to follow an F distribution. And maybe I'll just draw quickly for you here. The F distribution is something that looks sort of like this. Let's go with that. So it has a really long tail here on the right-hand side. It's asymmetrical. Some might say it looks kind of skewed to the right. Okay. The F distribution is always going to have 2 degrees of freedom associated with it. So there's sort of the first degrees of freedom and the second degrees of freedom. Okay. And whenever we get F statistics, if we want to work out the p-value, the area is always just going to be the area to the right of our test statistic. Okay, so we're no longer doing two-tailed tests. F statistics always look at only the area to the right. So maybe I'll just write in specifically, right? If this is our test stat, I'll just write in here the p-value is always the area to the right. Okay. And we'll go through an example of that. And in fact, we won't actually, when we do this ANOVA, R will do a lot of the calculations for us. So that won't really come into play too much because R will already know how to do it that way. But this statistic is based on this idea that we're comparing the variation or the variance between groups to the variance within groups. What does that mean? So let's kind of think about 2 sort of different scenarios. If the variation between is much larger than the variation within, okay, what would that look like? Well, maybe I'll draw these side-by-side box plots because those are kind of a useful thing, okay? So if I drew you 3 side-by-side box plots that look like this, let's say I had k groups, for example, 3 groups in this case, right? The variation within the groups, right? Here, there's not a lot of variation here, not a lot of variation here, and not a lot of variation here. Our variation within here is very small, okay? And the variation between, right, that's looking at how different these 3 are, right? It's quite large in this case, right? This one is very different than this one and very different than this one. So if you have very large between variation, especially in compared to a very small variation within, you end up with things that look like this, okay? This here is going to result in a much higher large F statistic. So maybe I'll even write that in. This is the means of the different groups are not equal, okay? And this is gonna end up with a large value for our F stat, okay? Alternatively, if the variation between and within are similar in size, then there's not going to be a significant difference between the two groups. So if I were to draw something side-by-side box plots that look sort of like this, right? They're all very, very similar. They have similar variation. They have similar variation within and between. You can kind of look at that and go, I don't really see that they're all that much different from each other, right? So something like this is going to result in a smaller F statistic, okay? And maybe not even significant, right? When we work out the p-value, it might have a really large p-value. Okay, but the same things are going to usually apply. So large test statistics are going to lead to small p-values. When we get small p-values, that means that we're going to reject the null hypothesis that the means are the same, and we'll have significant evidence for the alternative, that at least one mean is different. So a lot of the steps here follow the same. We have a null and alternative hypothesis, a test statistic that follows a particular distribution, right? We work out a p-value, and we're going to make the decision to reject or not reject. So a lot of the steps for our hypothesis testing are staying the same, very much that they always were. What we need to be careful in this case is obviously the way that we're calculating our test statistic is different, and we're going to go through exactly how to do that. And when we're thinking about the areas, because it's following this F distribution, we're always looking at the area in the right-hand tail, okay? But all the other steps sort of stay very, very similar.